Hi there! In the last lecture, we introduced transformers and self-attention. But I noticed that many of you found it a bit confusing. So I'm making this video to clarify things. I don't need to convince you why it's important to understand transformers. They're at the heart of all modern generative AI models. As data scientists, you probably won't be implementing transformers from scratch, but it's still useful to understand at a high level what's going on under the hood. In this video, I'll try to give you some intuitions about how transformers, especially self-attention, work. Let's start with the big picture of what a transformer does. What's the input to a transformer model? The input is a sequence of tokens, each represented by an embedding vector. In this example, for instance, the sequence of tokens is Nail the Quiz, and these are the corresponding embedding representations. What's the output of a transformer model? The output is a sequence of context-aware rich representations for each token. In this example, we are denoting these context-aware representations by H1, H2, and H3. Now you might be wondering, why is this output useful? This output is useful because in any language task, whether it's translation, summarization, question answering, or text generation, we need to understand the meaning of each word in context. And that's exactly what these output vectors H1, H2, H3 are designed to capture. Now let's connect this to language modeling. Suppose we want to predict the next word in this sequence, Nail the Quiz. We take the final representation H3, which is a vector of size D. To generate the next word, we pass this vector through an output layer. This output layer is also known as an unembedding layer. Why is that? Because we are going from a short and dense representation to a large vector of size vocabulary. Suppose V is the size of our vocabulary. Now what's going to be the shape of the weight matrix between hidden and output? It's going to be V by D. V is the size of our vocabulary and D is the size of our hidden vector. Now when we multiply this H3 by this weight matrix, we will get a vector of logits, where we will have a score for each word in the vocabulary. We then apply softmax on that vector to get probability distribution over all words in the vocabulary. Then we sample from this distribution to get the next word in the sequence. Let's look at this picture from the lecture notes, which shows a stack of transformer blocks. Each block builds contextual vector representations of the input tokens. The key idea is that these representations are built iteratively, layer by layer, so that each token's final representation captures not only its own identity, but also its relationships with other tokens in the sequence. In this example, we are starting with input tokens W1, W2, Wn. We are starting with some representations of these tokens, and we are calling these representations X1, X2, Xn. These representations are passed as input to layer 1. Layer 1 comes up with contextual representations H1, H2, Hn. These representations are passed as input to layer 2. Layer 2 builds richer contextual representations. We are again calling them H1, H2, Hn. These representations are passed as input to the next layer, and so on. Finally, after layer L, we have very rich contextual representations for all tokens in the sequence. Again, we are calling them H1, H2, and Hn. And the idea or our hope is that the final contextual representation for a token captures all kinds of meaningful relationships between that token and others in the surrounding context. Let's take a closer look at one transformer block or one transformer layer. Again, the input here is a sequence of tokens X1, X2, Xn, and the output is contextual representations of these tokens H1, H2, Hn. The most important component here is multi-head self-attention, which consists of multiple self-attention mechanisms running in parallel. So let's first understand self-attention, the core building block of transformers. What is self-attention? Again, similar to the big picture, our goal is to compute context-aware representations of tokens. Just like in the big picture, the input is going to be a sequence of tokens, and the output is going to be a sequence of contextual embeddings. I'm calling them H1, H2, H3 here. For each token, we want to figure out how much should I focus or attend to each of the other tokens when building my own representation. You can think of it like this. Each word is asking every other word, how relevant are you to me in this context? Let's consider our sequence of tokens, nailed the quiz. After passing through this self-attention layer, we want to compute contextual representations for all these three tokens, H1, H2, and H3. So what actually happens inside this self-attention layer? Let's start with the intuition. To find out which words are relevant to a particular word, we can use dot products to measure similarity between their representations. Suppose we want to compute the contextual representation of this token nailed. We might try taking the dot product between this input representation of nailed and all tokens in this sequence. So my first dot product is going to be input representation of nailed with itself, the input representation of nailed. My second dot product is going to be between input representation of nailed and input representation of the. And my third dot product is input representation of nailed and input representation of quiz. Now, which dot product will likely be the highest? Probably nailed and nailed because it's the self dot product. But that's trivial. It just tells us the word is most similar to itself, which isn't very helpful for understanding the overall context. To make this more meaningful, researchers proposed using different roles for the word we are focusing on and the word we are comparing it to. What are these roles? These roles are query role and key role, and we have a representation associated with each role. Nailed Q is the representation associated with query role, and nailed K is the representation associated with the key role. How do we compute these representations? We introduce learnable weight matrices, WQ and WK. With these matrices now, how do we compute nailed Q, this representation nailed Q? We take our weight matrix, WQ, we multiply that by our original representation of nailed, and that gives us this query representation of nailed. What's the dimensionality here? Let's assume that the original representation is 300 by 1. And we want this representation to be 100 by 1, this query representation to be 100 by 1, and key representation to be 100 by 1. Then WQ is going to be 100 by 300. Our original representation of nailed is 300 by 1. So dimensionality of nailed Q is going to be 100 by 1, and that's what we want. Similarly, we can calculate our key representation of the word nailed. We take the key weight matrix, we multiply that by the original representation of nailed, and that's going to give us key representation of nailed. Now we have to calculate key and query representations for all tokens in our sequence. For the token nailed, we have these two representations, nailed Q and nailed K. For the token the, we have these two representations, the Q and the K. And for this token quiz, we have these two representations, quiz Q and quiz K. Note that the matrices WQ and WK are shared across these tokens. So we are using the same WQ and WK matrices to come up with these two representations for all tokens in our sequence. Now we are ready to compute dot products to get meaningful similarities. How do we do that? Suppose we want to compute contextual representation of this token nailed. We take query representation of this token nailed and we take its dot product with key representations of all tokens in the sequence. So my first dot product here is nailed Q and nailed K. Suppose that dot product is 1. I'm assigning a low score here because this word nailed K, this key representation of the word nailed, it's not going to be that helpful to understand the meaning of nailed in the given context. My second dot product is nailed Q and the K. I'm assigning a score of 2 here. And my third dot product is nailed Q and quiz K. I'm assigning a high value here because the word quiz is going to be very useful to understand the meaning of nailed in this context. Now, these are just 3 attention scores. We then apply a softmax to these scores, turning them into a probability distribution. So I do something like softmax and I have these 3 scores. Here I'm showing you the probabilities after applying softmax. What do these probabilities mean? These probabilities are attention weights which tell us how much nailed should focus on each word, including itself, when computing its final contextual representation. Now that we have the attention weights, we are ready to compute the contextual embedding for the token nailed. For this, we introduce a third type of vector, the value vector. Just like before, we compute value vectors by multiplying the input embedding with a third learnable matrix, WV. Here, for example, we are taking input representation of nailed. We will multiply that by this matrix WV and we get this value representation for the token nailed. Here we have value representation for the token the, and here we have value representation for the token quiz. What do we have so far? We have our attention scores for nailed Q and we have value representations for all tokens in our sequence. With this information now, the context-aware representation for nailed is a weighted sum of the value vectors using the attention weights we just calculated. So this H nailed, which is contextual representation of nailed, is going to be 0.017 times this value representation of nailed plus 0.047 times this value representation of the plus 0.936 times this value representation of quiz. Now remember, each of these representations are vectors. Suppose these are 100-dimensional vectors. Then our final representation is also going to be this 100-dimensional vector. So that's how we calculate this d-dimensional vector that reflects not just the identity of nailed, but also its meaning in the context of the given sequence. Similarly, we create context-aware representations for the tokens the and quiz. For example, if we want to create context-aware representation of quiz, then we take query representation of quiz, we take dot products of this representation with key representations of all tokens in the sequence, we apply softmax to get attention scores, then we use value representations and these attention weights to create context-aware representation for the token quiz. Let's summarize the self-attention mechanism. For each token, we compute 3 vectors: query, key, and value. To build a contextual representation for a token like nailed, we use its query vector and we compute dot products with the key vectors of all tokens in the sequence. Then we apply softmax to turn these scores into probabilities. These are our attention weights. We use these weights to compute a weighted sum of the value vectors, resulting in a context-aware representation.